All right, listeners. So today we are diving into some pretty complex stuff, substructural logics. And you actually sent over this excerpt from the Stanford Encyclopedia of Philosophy on this topic. And wow, it is a real philosophical roller coaster. So get ready to rethink some of your most basic assumptions about logic.
Yeah, you're not kidding. Substructural logics really challenge the foundations of how we reason. It's like we're questioning the rules of the game itself.
Okay, so for our listeners who might be thinking, substructural what? Let's start with the basics. Like, usually we take for granted certain rules in logic, right? The ones that tell us how to combine premises and reach a conclusion. But substructural logics, they mess with those rules, right?
That's it. These rules are called structural rules, and they operate at a much deeper level than just those specific connectives. Like and, or, if, then. They're about the framework of logic itself.
So it's not about the content of the arguments, but the machinery underneath.
Exactly. They're about how we put arguments together, regardless of what those arguments are about.
I see. And the Stanford Encyclopedia actually uses modus ponens and Barbara as examples to show what a structural rule isn't. Can you break that down for us?
Sure. So like modus ponens, for example, it says that if we have if P, then Q, and we also have P, then we can conclude Q. And that rule is all about the condition, the if-then. It doesn't tell us anything about handling premises more generally.
Okay.
Same with Barbara. That's a rule from syllogistic logic. And it only applies to arguments with these universal claims, like all dogs are mammals.
Gotcha. So those are rules about specific logical content, whereas structural rules are more like the backstage crew, making sure the whole logical show runs smoothly.
Yeah. A great analogy. And the Stanford Encyclopedia points to the cut rule as a prime example of a structural rule. This one is all about how we use derived information in proofs.
Okay, so let's unpack cut a bit.
Yeah.
Why is it so important in the context of substructural logics?
Well, the cut rule basically says that if you can prove A from some starting point, and then you can use A along with some other stuff to prove B, then you should be able to just directly prove B from all the initial information combined.
So it's like a shortcut in a proof. If we know that A is a consequence of our assumptions, then we don't need to reprove it every time we want to use it.
Exactly. And this actually has justifications from both proof theory and model theory. So proof theory sees cut as reflecting our ability to combine proofs modularly. And from a model perspective, if every model that satisfies the initial premises also satisfies B, then the argument is valid regardless of the steps in between.
Okay, this is already making me question everything I thought I knew about proofs.
Mm-hmm.
But substructural logics, they actually challenge some of these rules. Right? It's like they're saying, hold on, what if we tweak the rules of the game a little bit?
That's it. They question assumptions like weakening commutativity, associativity, and even contraction things we usually take for granted in classical logic.
Whoa, that's a lot to unpack. Let's break down these assumptions one by one, starting with weakening. What exactly does that mean, and why would anyone want to reject it?
So weakening basically says that if you can derive a conclusion from a set of premises, adding more premises won't change that. It seems intuitive.
Right. If I can bake a cake with flour, eggs, and sugar, adding a bag of chips to the mix isn't going to stop me from baking that cake, even if the chips are totally irrelevant.
Perfect example. But proponents of relevant logics, they would argue that this kind of reasoning isn't always valid. They say there needs to be a genuine connection, a relevance between the premises and the conclusion. Adding irrelevant stuff should weaken the argument, not strengthen it.
So in relevant logics, it's not just about the conclusion being true. It's about whether it's justifiably true based on the premises. It's about the relationship between the ideas.
Precisely. So think about the material conditional in classical logic. If P then Q is considered true whenever P is false or Q is true, and this leads to some weird results, like a true statement implies anything.
So even if the sky is blue is true, it shouldn't logically imply pigs can fly, even though technically, according to classical logic, it does.
Exactly. Relevant logics, by rejecting weakening, they try to make sure that the premises actually contribute to the conclusion.
So they demand a much tighter connection between the ideas.
Right.
Wow. So we're already questioning what I thought was a fundamental principle. I can see why this is interesting to a philosopher. What about commutativity? What is that all about, and why would we want to mess with it?
Well, commutativity assumes that the order of the premises doesn't really matter. So in classical logic, P and Q is the same as Q and P, but some substructural logics would challenge that.
Hold on. So the order in which we present information could actually change the logical outcome.
Yeah. Think about modal logic. So saying it is necessary that if John is a bachelor, then he is unmarried, which is true. It doesn't mean we can just flip it and say, if John is a bachelor, then it is necessary that he is unmarried. The first one is about the necessary connection between bachelorhood and being unmarried. The second one is about John's specific situation.
Ah, I see. The order changes the meaning, even though we're using the same words. And the Stanford Encyclopedia mentioned that rejecting commutativity can lead to two different types of conditionals, right?
Yeah, we might have a left to right conditional, like an arrow pointing to the right, and a right to left conditional, an arrow pointing to the left. Each of them behave differently when premise combination isn't commutative.
This is getting really deep. We're not just changing the content of logic, we're changing the very structure of how we think.
Yeah, and we're just getting started. There's also associativity. So this rule is about how we group premises together in classical logic. We assume that P and Q and R is the same as P and Q and R, but substructural logics might challenge that as well.
Oh, wow. So just like with the order of premises, the way we group them could actually change the logical outcome. It's like we're getting down to the nuts and bolts of how we structure our thoughts.
Exactly. It might seem like a minor detail, but it can have big implications. Imagine a proof where a rule requires a specific grouping of premises. Well, without associativity, you might not be able to rearrange them as needed.
It's like trying to solve a math equation where you can't rearrange the parenthesis.
Right. And then we come to maybe the most radical challenge of all rejecting contraction. So this rule allows us to use a premise multiple times in a derivation.
So if I use the premise all humans are mortal twice to conclude that Socrates and Plato are both mortal, I'm relying on contraction.
You got it. But logics, like linear logic, see this as problematic. They view each premise as a resource that can only be used once.
Oh, like a magician using a rabbit for a trick. Once the rabbit's out of the hat, it's gone. You can't keep pulling it out over and over again.
Exactly. In linear logic, you have to keep track of how many times you use each premise and leads to a whole different way of thinking about proofs, almost like a game of logic where you have to manage your resources carefully.
So we've gone from questioning the order of premises to treating them like these finite resources.
Mhm.
This is really making me rethink how I approach logic. But I have to ask, are these substructural logics just abstract thought experiments for philosophers, or do they actually have applications in the real world?
That's a great question, and the answer might surprise you. Substructural logics are far from just theoretical curiosities. They actually have a variety of practical applications in fields like computer science, linguistics, and even artificial intelligence.
Oh, wow. Okay, now you've got my attention. Tell me more about these applications. What kind of problems can substructural logics help us solve?
Well, we've already touched on relevant logics, which focus on making sure that the premises are genuinely connected to the conclusions. And these have applications in areas like philosophy of language and artificial intelligence, where understanding the relationship between information is crucial.
So if we're building a chatbot that needs to understand the context of a conversation, relevant logics could help us prevent the chatbot from making these illogical leaps in reasoning.
Exactly. Then there's linear logic, which, as we discussed, models resource use, and this has applications in computer science, particularly in areas like concurrency and resource management.
So if I'm designing a system where multiple processes are competing for the same resources like memory or processing power, linear logic could help me avoid conflicts and make sure everything runs smoothly. It's like a traffic cop for my computer program.
A very apt analogy. And then we have the Lambert calculus, which focuses on the order and composition of linguistic elements. And this has been hugely influential in computational linguistics, particularly in parsing and understanding sentence structure. It's like grammar rules for computers.
So all these different logics, which might seem quite abstract at first, can actually help us build better computer programs or understand language more deeply and even design more intelligent machines.
Precisely. And what's fascinating is that all of these logics, which were initially developed quite independently, have now sort of converged into this unified field of study. It's like they were all speaking these different dialects of the same logical language, and now we're starting to understand the grammar that connects them all.
That's amazing. It seems like substructural logics are really opening up this whole new world of possibilities for understanding how we reason and how we interact with the world around us.
Yeah.
But how do we even study these logics? What are the tools and techniques we can use?
Well, there are two main approaches, proof theory and model theory.
Can you give us like a quick rundown of what those are and how they apply to substructural logics?
Sure. So on the proof theory side, we have systems like natural deduction and Gensen systems. These allow us to formally represent and manipulate arguments in these logics and even prove things about them. For instance, we can figure out if a given substructural logic is decidable, meaning is there an algorithm to determine if an argument in that logic is valid or not?
So we can actually figure out if there's a foolproof method for checking the validity of arguments in these systems. That's pretty powerful.
It is. And then we have model theory. This approach gives us tools to interpret these logics in terms of formal structures. And the Stanford Encyclopedia mentioned these structures called Routely-Meyer models in connection with the relevant logic R.
Right. Can you unpack that a bit? What are these models all about, and how do they help us understand substructural logics?
Well, instead of the usual binary relation between possible worlds that we see in modal logics, we have this ternary relation. It's like adding another dimension to our logical space. And this relation captures the way that premises combine to support conclusions.
So instead of just saying A supports B, we're saying A in a specific context with C supports B. It's like we're adding this extra layer of nuance to the relationship between propositions.
Exactly. And by imposing different conditions on this ternary relation, we can capture the behavior of different substructural logics. For example, if we want a logic where the order of premises doesn't matter, a commutative logic, we would impose a symmetry condition on this relation.
So the properties of this relation determine the flavor of the logic we're dealing with. We can fine-tune the logic by tweaking the rules of the relation.
That's a great way to put it. And by interpreting this relation in different ways, we can apply substructural logics to different domains, for example. We can interpret it as representing the application of functions to data, which connects substructural logics to the world of computation.
Wow. So we can actually use these models to connect these abstract logical concepts to concrete applications. It seems like substructural logics are more than just this philosophical curiosity. They're actually a powerful tool for understanding a wide range of phenomena.
Absolutely. And there's another fascinating aspect to these logics that we haven't even touched on yet, the challenge of quantifiers.
You mean those logical expressions like for all and there exists? Those seem pretty fundamental to any logical system. What kind of challenge do they pose in the context of substructural logics?
It turns out that like the usual axioms and rules for quantifiers that we use, the ones that seem pretty straightforward in classical logic, well, they don't always play nicely with the models that we use for substructural logics.
So what we think should be true about for all and there exists in these logics doesn't actually match up with how they behave in the models. That sounds like a real headache for logicians.
It is. It's a really active area of research. People are trying to come up with different semantics for quantifiers that fit better with the spirit of substructural logics. Think of it like trying to find the right puzzle piece. We have these powerful logical systems, but the standard quantifiers that just don't quite fit in the way that we'd expect.
I see. I'm starting to see why substructural logics are considered to be this rich area of exploration. There's like all these interconnected challenges and puzzles. But you mentioned one more twist, something about rejecting even more fundamental rules. That's got to be pretty wild.
It is. We've been talking about logics that reject structural rules like weakening and contraction and so on, but there are some logics that go even further and they reject the cut rule and even the identity rule.
Wow, a cut allows us to use derived information. It seems so essential to like how we reason, and identity just says that any proposition implies itself. Are you telling me that there are logics that throw those out the window?
You heard that right. These logics might seem extreme, but they offer some pretty intriguing possibilities for dealing with philosophical puzzles like paradoxes and vagueness.
Okay, I'm officially on the edge of my seat. Tell me more about these rule-breaking logics. What's the motivation for rejecting something as basic as cut?
Well, remember how we talked about relevant logics, wanting to make sure that the premises are genuinely relevant to the conclusion? Well, some philosophers, they take this idea even further, and they argue that unrestricted cut can actually sneak in these irrelevant conclusions. So they propose these logics where the premises have to be very tightly connected to the conclusion for an argument to be valid.
So no more logical free riders. Every premise has to pull its weight.
Exactly. One example is Neil Tennant's core logic, which rejects unrestricted cut to ensure that conclusions are genuinely supported by their premises. But it's important to note that core logic still allows for a restricted version of cut, so it doesn't become too weak.
That makes sense. It's like finding the right balance between keeping the logic powerful enough to be useful, but also making sure it doesn't let in any irrelevant conclusions.
Right, and then rejecting identity is even more radical. This rule just states that any proposition implies itself seems pretty obvious, right? Like saying, if it's raining, then it's raining.
It does. What could be more basic than that? I'm really curious to see how you could justify rejecting something so fundamental.
Well, logics like TS actually challenge this seemingly unassailable principle. And by rejecting identity, they open up new ways of thinking about concepts like vagueness and truth.
Hold on. How does rejecting identity help us with those tricky concepts? It seems like it would just make everything more confusing.
Think about a vague predicate like tall. Where do we draw the line? Is someone who's 5'11" off tall? What about 5'10"? By rejecting identity, we can allow for cases where a proposition and its negation are both somewhat acceptable. It reflects this inherent ambiguity of vague concepts.
So instead of forcing a sharp yes or no answer, we can have degrees of truth or acceptance. That's interesting.
Exactly. And this approach has implications for dealing with paradoxes as well, like the liar sentence, this sentence is false. By rejecting identity, we can avoid those explosive contradictions that arise from these self-referential statements.
So logics without identity give us a way to contain the damage caused by paradoxes. They provide a sort of safety valve for our reasoning.
Yeah, in a way, but here's where things get even more mind-blowing. ST. The logic that rejects cut actually has the same provable sequence as classical logic, and TS, which rejects identity, has none.
Wait, that doesn't make sense. How can we say these are different from classical logic if they either prove the same things or prove nothing at all?
That's the beauty of it. It's not just about what they prove at the level of those individual sequence, those strings of symbols representing arguments. It's about the relationships between sequence. We need to look at these meta inferences between inferences.
Okay, I'm feeling a bit lost, but definitely intrigued. Can you explain meta inferences a bit more? It's like we're going up a level in our logical analysis.
Think about it this way. Even though ST proves the same sequence as classical logic, it rejects the cut rule, which is a meta inference. So this means that it has a different structure of reasoning, even if the end results might look similar.
So it's like two chefs making the same dish, but using different cooking techniques. The final product might taste the same, but the process behind it is completely different.
A perfect analogy. And with TS, even though it doesn't prove any sequence directly, we can still study the relationships between sequence and explore the patterns of reasoning that it allows. It's like investigating the blueprint of a building, even if the building hasn't been constructed.
Wow, so these seemingly bizarre logics were actually opening up this whole new level of logical analysis. We're not just looking at individual arguments anymore, but the relationships between arguments and the overall structure of reasoning.
Exactly. And this exploration of meta inferences has led to the realization that, we can actually have different grades of validity, not just at the level of formulas, but also at the level of sequence and meta inferences.
So instead of just saying an argument is valid or invalid, we might have this spectrum of validity, like saying it's strictly valid, tolerantly valid, or something in between. It's like adding shades of gray to our black and white view of logic.
Exactly. This allows us to capture the nuances of logical reasoning in a much more fine-grained way. It's like having a high-resolution image instead of a blurry one. We can see so much more detail.
So what does this all mean for our listener, the philosopher grappling with complex ideas and challenging arguments? It seems like substructural logics are more than just this technical curiosity. They're offering a new perspective on the nature of logic itself.
You got it. It means that the world of logic is far richer and more diverse than we might initially assume, and by questioning even the most fundamental assumptions about how logic works, we can discover these new tools and frameworks for understanding the nature of reasoning language and even reality itself.
This deep dive has been a real mind-bender. We started by questioning a few basic rules and ended up exploring this whole universe of alternative logics with applications in everything from philosophy and linguistics to computer science and artificial intelligence.
It really has, and substructural logics provide this powerful reminder that questioning assumptions is truly at the heart of philosophical inquiry. And by challenging the status quo, we can open up whole new vistas of understanding.
So listener, the next time you encounter a logical argument, take a moment to consider that underlying structure. What assumptions are being made, what rules are being followed. You might just discover a whole new way of thinking about logic and its implications for the world around us.
And remember, there's always more to explore. The world of substructural logics is constantly evolving, with new discoveries and applications emerging all the time. It's a fascinating journey for anyone willing to dive in and challenge their assumptions about how we reason and make sense of the world.
Until next time, keep those philosophical gears turning.